3. Table shows number of male and female students enrolled in nursing at the University of Oklahoma Health Science Center for recent semester. A student is selected at random. Find the probability of each event. Part A says they want the probability. When I write out these probabilities, I always write it out so that I can understand it. Might not be the greatest thing mathematically, or the greatest way mathematically to write it out, but I write out something like male or a nurse. So write it out so that you can understand what you're looking for. So the first thing we look at is a male. Well, we look at males. There's 1,255 males out of the total of 3,964. Is that right?
Yeah.
Then we're going to find, it says or nurse, so we're going to add on probability that you have pick a nurse, somebody that's a nursing major, which there's 1,167 of them out of 3,964. The problem with that is, if we just add those two probabilities together, we're counting some of those people twice. And what people are we counting twice? The male nurses, right? The ones that are male nurses. How many male nursing majors do we have? So we got to subtract off that 151 out of the 3,964. Put all that together. I'm going to run out of space over there. All you really have to do is add these two, then subtract that one, then take that answer and divide by 3964. What's it come out to be? 0.572. Part B. Go out 3 spaces on these. Usually when we're doing these probabilities, we want to go out 3 spaces. I think I've mentioned that during this chapter, but go out 1. So if we were going to write it as a percent, we'd have something like 52 or 57.2%. So you always want to go out that 1 extra space. Part B, the student is female or nursing major. Female or nurse. How many females do we have? 2,709. How many nursing majors? We just did that, didn't we? 1167 out of 3964. Now again, we could have female who is a nursing major, so we got to subtract that off. How many females are nursing majors? 1,016. Add these two together, subtract that, get that answer, then divide by that 3964, what you come up with. Sound right. Did I read the problem wrong? Back up. 23. Yep.
0.7.
Sure did. I read this wrong. This says not a nursing major. My fault. So 1167 is wrong. How many? So that's how many were nursing. How many are not nursing majors? 2,797. Now let's,
Female nurses?
no. It says female or not a nursing major. So don't put the two things together. So now do that. What do you come up with? messed that up too, didn't we?
I was about to say, 'cause I have like a 1.13. It's like, that's not right.
So we gotta take out people who are females and not nurses at the same time. So how many females that are non-nursing majors do we have? So that should be 1693 on top there. Should read more carefully, shouldn't I? Make this problem a whole lot easier. Nine, 6-1. That sounds a little better. Part C, I'll read more carefully this time. Student is not female or is a nursing major. So not female or nursing major.
Does it say not a nursing major or?
No, this time it says a nursing major. Not female, well that's, if you're not a female, then you're what? So that's the same as this one, right? That's 1255 over 3964 plus the nursing major we did, which was right here. If you were a nursing major, 1167 out of 3964. Then we got to subtract off the not. I wrote down not female, right? Not female. We want those people who are not female, so the males that are nursing majors, we're going to take that away. So who are the males that are nursing majors? How many of them? Out of 3964. Do that. 0.572. Part D. Are the events being male and being a nursing major mutually exclusive?
Yeah.
No. Not mutually exclusive, because they could happen at the same time. Next question. Probably a test into this week. So it might be a good idea if some of you, especially if you've been absent and you've missed some assignments, maybe pay a little bit of attention. 18. Rolling the die. Says you want to roll a 5 or a number greater than 3. So again, I write it. We want to roll 5 or something greater than 3. What's the probability of rolling a 5? 1 out of 6 plus what's the probability of rolling a number bigger than 3? 3 out of 6. 3 out of 6. But then we got to subtract off things if they overlap each other. So is a 5 greater than 3? So we got to subtract off 1 out of 6. Well, what happens with these 1 out of 6s? They just sort of cancel each other out. So what are you left with there? Half. I would leave it as a fraction. This book again changes everything to a decimal. I wouldn't change that to a decimal. It's better for probability to say, okay, we're going to win 1 time out of every 2 times that we play. Next one says probability of a number less than 4 or an even number. So we want a number less than 4 or an even number. Again, to write it out this way isn't mathematically correct, but if it helps you to look at it this way, it always helps me to know exactly what I'm looking for. I'm not worried about being mathematically correct. What's the probability of getting a number less than 4? 3 out of 6. Plus, what's the probability of getting an even number? 3 out of 6. Minus, do those two overlap any? What do they share? 2. So there's 1 out of 6, right? What do we get? 3 plus 3 minus 1. 5 out of 6. Again, I would probably just leave it that way instead of changing it to a decimal. If you wanted to change it to a decimal, 5 out of 6 is what, like 0.83 something or something like that? 3. Letter C. Rolling a 2 or an odd number. So we want 2 or odd. What's the probability of rolling a 2? 1 out of 6. What's the probability of rolling an odd number? Nobody knows the probability of rolling an odd number? 3 out of 6. Now, this time, do we have to subtract off? Are these events mutually exclusive? Yeah, these are mutually exclusive, so we don't have to subtract this time. What's 1 plus 3? And that reduces to what? 2 out of 3. So when they're not mutually exclusive, we got to subtract that where they overlap each other off. Where they are, or when they are mutually exclusive, we don't have to do the subtraction. Next question. 21. 21. Number of responses to a survey are shown in the Pareto chart. The survey asked 1,026 U.S. adults how they would grade the quality of public schools in the United States. Each person gave one response. Find each probability. Part A says, does everybody remember what is a Pareto chart?
The one that goes from highest.
It goes from highest to lowest. So the one gets the most to the lowest. So on this one, want a person who did not give the schools an A. So probability they didn't give an A. Do we really want to go through and add up all those probabilities that where they didn't give them an A? What would be easier?
Total minus 3.
What do we know the total probability always is? Or if we're doing decimals, just one whole, right? So 1 minus the probability that they did give an A. That's what we're going to actually find here. That's the easiest. Somebody help me out. What is the probability that they, or number of people gave an A? 52 out of 1,026. On your calculator, if I was doing this on the calculator and I wanted the decimal answer, what I would do, I'd just take 52 divided by 1026 and then hit minus 1. That's going to give you a negative, but what do you know about the sign?
Don't matter.
You don't want the sign. So do this divided by this, then subtract 1 and just change the sign back to positive. What's it come out to be? 0.949?
Yeah.
So about 95% of all people didn't give public schools that were surveyed, didn't give public schools an A. Randomly selecting a person from the sample who gave public schools a D or an F. So we want probability that they gave a D or an F. How are we going to find the probability that they gave a D? Or what is the probability they gave a D? Plus, what's the probability they gave an F? 398,
126.
126. I think you were given the total. Now, are these two events mutually exclusive? Or do we have to subtract something off? They're separate, right? Nobody gave a D and gave an F at the same time. So all we gotta do is add those two together. And Brendan already told us that's 398 out of 1026. Because that makes no sense to me. If I say, yeah, 398 people out of 1026, tell me what that is as a decimal.
0.38.
So about 39% of the people gave public schools a D or an F. More than a third of the people gave them a D or an F. Gotta be able to tell if events are mutually exclusive or not mutually exclusive. Last section in this chapter, section 3-4. We're gonna, two main things here. Determining the number of ways a group of items can be arranged, or determine the number of ways to choose several objects from a group without regard to order. Use accounting principles to find the probabilities. These two things are permutations and combinations. Those are the things that we're going to do today, and you will be confused because it is hard to decide. Hey, is this a permutation or is this a combination? So you got to listen closely. Speaking of which, we'll probably have another symbols test or quiz coming up here real soon. Probably next class. Just to give you a heads up, because you've annoyed me today. So. Permutations. You gotta listen closely and you gotta understand what you're doing differently here. If I have all these books laying here and I'm doing permutations, that means when I go to stick them on the shelf, I want all the different orders that I could put all these books on the shelf. Alright? So I want all the different ways. That'd be one way, right? If I took this book out, moved it right here, that'd be a second way. Do I really want to go through here and try to do all this? There's so many of them that it's hard, right? But you got to understand that permutations are when you're doing something in an order. Now, Miss Clark asked about this already. N factorial. That's how that's read with the exclamation mark. Factorial is telling you to do this. I know this is sort of confusing looking at it this way, but if I did something like 5 factorial, all that means is that you take the number that you start with right there, 5, times it by the next number down, then times it by the next number down, till you get to 1. So you multiply it all out, all the way down to 1. So if we did 15 factorial, that means 15 times 14 times 13 times 12 times 11 times 10 times 9, all the way down to 1. Probably not something you want to do right now once you get to this point. So you're going to need to make sure that you have your calculators. A lot of this, we haven't used the calculators a lot on this chapter yet. But if you look on your calculator, if you hit the math button, I think, and you go over to probability, so you have the math button, and you want to scroll over till you get to probability, and you look down through there. The fourth one on my calculator, I don't know, it might be different on some of the calculators. Is it the fourth one?
Yep.
The fourth one is that factorial. Now you'll also notice, you see the second and the third one, where it says NPR and NCR. Make sure you can find those, because that's the other part that we're going to talk about today. What do you think the P stands for then if you did them last year? Permutations. So this is permutations. All right? Now, if we're taking all these books and we're lining them up, then all we got to do is take 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 books here. So we just take 9 factorial. And that would tell us how many different ways we could line up all these books. If, when we get on down here in a second, if we don't want to take all 9 of them, let's say we only got room on our shelf for 7 of the books, and we want to know how we can put those 7 on there, and we're going to throw the other 2 out. That's where this comes in. All right, so we're still doing permutations because we're seeing how many different ways we can put those books on the shelves. How many books did we have to choose from originally? 9. So that N right there in the front, that little subscript is 9. The R, how many are we actually keeping? 7. And we're going to put that into our calculator, and it's going to tell us that.
181,000.
Big number still, right? Now, if I said, what's the probability that I put the books in this order on my shelf? How many different orders do I have right there? There's only one time that it's going to be in that exact order, right? So it'd be 1 out of whatever that big, huge number that you just said was.
181,000.
So 1 out of 181,000. We'll talk more about that here in a second. Did you do it wrong?
No, I did it wrong.
How do you put it into your calculator?
I'm going to show you here in a minute.
Put the numbers in.
0 factorial. Got to remember this because some of the stuff that we do today is going to have 0 factorial. 0 factorial is 1. This is one of those math rule things. You got to know this. That it just works out this way. It's the way that we have to do. There's a couple different things in math that don't really physically make sense. But for our patterns in math, we have to make them make sense by doing something like this. 0 factorial is always 1. So, because if I did something like 1 factorial, that gives me 1. If I did 2 factorial, that gives me 2. If I did 3 factorial, that gives me 6. To go backwards, if we were going to do things below the line down here, that has to be the way it works out. The one pattern that you've probably seen in Algebra 2 or someplace like that is if I did something like this. 1 squared, 2 squared, 3 squared, 4 squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 16. Now if I went backwards and you got like 1/2 squared, this is 0, right? When you move backwards, there's a pattern there. And to go along with that pattern, you have to follow a certain thing. And there's just a couple of rules in math, and I don't know why I'm talking about that. Don't really need it. But there's a couple of rules in math that you need to be able to say, well, hold on now, we need to put something in there to fit the pattern. And that right there is one of them. The other, just make sure on this, make sure you factorial guaranteed. You'll see that symbol on any symbols test that we have from here on out probably. You got to know that it means factorial. I would just accept just the word factorial is good enough. You don't have to explain to me what it is. Just the name of it's factorial. The objective of a 9x9 Sudoku number puzzle is to fill the grid so that each row, each column, and each 3x3 grid contains the digits 1 to 9. How many different ways can the first row of a blank 9x9 Sudoku grid be filled? So we're looking at just this first row. So let's say you like to do Sudoku puzzles. I think when I made up this PowerPoint, Sudoku was a bigger thing about 5 or 6 years ago. Everybody was doing it, and now it sort of went away. How many different possible puzzles are there for this first grid right there? How many different choices do you have for the first number? 9 factorial.
8.
I'm sorry, 9. How many for the second number?
8.
8. How many for the third number? 7. Does everybody see why I messed up there and said 9 factorial? Because what are we going to do here? We're just doing it out. It's 9 factorial. Since we got 9 things there, we're just going to go all the way down to 9. When we get to the last block, how many different choices do we have? There's only one. Again, if you grab your calculator and you put in 9, then you go to the math button, go over to probability, go down to factorial, hit enter, and it says 9 factorial, then hit enter again. 362,880. So there's 360,000 over 360,000 different ways that you could, if you're making up those Sudoku puzzles, that you could make that first line. You don't know what Sudoku is? So see how you got 9 blocks going this way, 9 blocks going this way? So this has to be like, let's say we have 1, 2, 3, 4, 7, 8, 9 there. This one down this way has to have those numbers. You can't have the same number in this row or this column. You can't have the same number repeated twice in that column.
You got 2 and 3 in the same box.
You can't have the same number in those 9 boxes. So I've already messed up because we got 2 2s and 2 3s in that box, so mine won't work. And all the rows and columns and all those little, see how this little 9 square box right there is none of them can have the same number in it more than once. Factorial just showed you that on the calculator. This is important. This is how you're going to do this. So Jacob's going to watch here in a minute because he has asked how do we punch it into the calculator. I'm going to show him.
I have it.
That's good. Permutations of n objects taken r at a time. So you got total number of objects is n. Your n is how many total objects you have. R is how many you are taking. This here at the end of this formula says where r is less than or equal to n. So r and n could be the same thing, but r can never be bigger than n. Because I can't have 9 books here. Can't have 9 books and say I'm going to take 15 books. That doesn't make sense. All right? So if you only got 9 books, then how many you're taking can't be more than that. You know, Sophie probably sometimes goes ask her folks for some money. Said, I need some money. And Mom says, I got $10 in my purse, but I need 20. Mom could say, think of permutations here, Sophie. If I only got $10, you can't take 20. It doesn't work.
I didn't even know this was a word.
Do what? Oh, you didn't know it was a word. On this formula, write it out, number of items that you have to pick from, you're doing permutations, how many you're taking at a time. One I use all the time is our seating chart in here. All right? How many different seating charts could we make up? I'm taking from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, plus we're missing 4, so 14 students. So my permutations, it would look like this. Choosing from 14, well, how many people am I putting in the seats? 14. I'm doing all 14. All right? When I plug into here, this top number then is going to be 14. This number n is going to be 14. The r is going to be 14. What is on bottom here? What's 14 minus 14? 0. So we end up with 0 factorial. You can't divide by 0, so that's why we say 0 factorial is 1. All right? So all this is really going to end up, when I make out a seating chart, all it really ends up is I take all 14 of you and I put you in a seat, so it'd just be 14 factorial. That many different ways that I could put you in the seats in the classroom.
What's that? What's that? Army. What are you saying up there?
Taking. So this is your total number. How many items you have to choose from. And this is how many you're taking each time. Let's say a deck of cards. We'll go back to the Go Fish, all right? I think when you play Go Fish, don't you get, how many cards you get when you play Go Fish? 7? 7, I think, right? So we would want our permutations. How many different things, different orders could we get of these cards? Well, how many cards are we choosing from? 52. How many are we taking at a time? All right. So we could do that on our calculator. To punch it into our calculator, all you're going to do, hardest thing when you're doing permutations and combinations is remembering on your calculator, you got to put that number in before you go to the math button. So you put in, and I forget it all the time. So you put in 52, then you go to the math button, go over to probability, go down to permutations, put in 7, then hit equals. And it gives you a number that looks like this. And we're going to have a whole lot of these, so you got to know what this scientific notation means. And then it says E11. What's that tell you? That means you're moving this decimal over how many places? 11 places. Notice the 11's positive, so you're moving in that direction. So it'd be 6. And we won't go out all these places. We'll probably usually stop like right about there. So it'd be 6, 7, 4. That's 2 places. How many more zeros do I need? 9. 3, 4, 6, 7, 8, 9. So when we're playing Go Fish with our mommies, different hands that we could get is about 674, what is that, billions?
A lot of combinations.
A lot of what?
Permutation.
Now, Malachi was probably right, even though I corrected him. This probably isn't permutations, this would be more combinations, and we're getting ready to get to that here in a second. Because when Malachi's holding his cards in his hand, and he's got all 7 of his cards in his hand, does he care if the 3 is here and the 5 is there, or if they're switched around? No, it's still the same cards, right? So, and that's where permutations and combinations sort of switch. Example of finding this. Find the number of ways of forming a 3-digit code in which no digit is repeated. No digit is repeated. So if we're doing a 3-digit code, a lot of times I'll do this if I'm doing one of these problems. I draw 3 blanks because I have 3 digits. What could we possibly have for this first 1-digit number? What are the numbers you could have? 1, 2. So now you got to be careful because everybody always leaves this other number out.
0.
0. So how many different possible first numbers are there? 10. A 3-digit, we want a 3-digit code which no digit is repeated. So how many possible choices for this one? 9 and 8. We really don't, we could use permutations for this. It's sort of unnecessary because we could just do it this way. 10 times 9 times 8. What's that give you, like 720? Now if we use permutations, how many numbers do we have to choose from? 10. How many are we taking at a time? 3. Let's use our calculators and see. Hopefully it comes out to be 720 if we do that. Otherwise, I'm messing up somewhere.
Yeah, it does.
So it does?
Yep.
So we've gotten 10 numbers. We're picking them 3 at a time. 720 different possible ways. If it's just a short one, like this one was, where there's just 3 numbers that you're picking, it's probably easier just to do this. 10 choices for the first one, 9 choices for the second one, 8 for the third one. We're using the fundamental counting principle that we learned last class or class before, whichever it was. Fundamental counting principle. 10 choices for the first one, 9 for the second one, 8 for the third one. What if they'd said that the digits could repeat? Then it'd be 10 times what? 10 times 10. We couldn't use permutations then because permutations doesn't work that way. If I take this book, I can't take that book the second time and that book the third time. It can only appear there once. Now, I did it out longhand here. If you do it out longhand, look at what happens. Maybe you don't have a calculator one day and you need to do it out longhand. We got 10 factorial on top. We got 10 minus 3 factorial on bottom. So we end up with 10 factorial. Watch closely on this, because this way it makes sense to you. 10 factorial on top, 7 factorial on bottom. Well, if I write that out 10 times all the way down to 1 and 7 times all the way down to 1, look at what happens from 7 down on both top and bottom. They just cancel out. Alright, so all we're actually left with is 10 times 9 times 8. That's what we did up here. So when you're doing permutations, that stuff cancels out if you're doing it out longhand. Don't make doing it longhand hard just because if you use the calculator, it makes it easy. Because the bad thing with the calculator is, if you punch something in wrong, you're going to write down that answer because you're going to think it's right no matter what because the calculator gave it to you. So if you know what you're doing and you can work it out longhand, it might be very helpful. 43 race cars started the 2007 Daytona 500. How many ways can the cars finish first, second, and third? So again, we're doing permutations. What's our number that we're picking from? 43. How many are we taking at a time? 3. Now, if I do this out longhand, it was 43 factorial on top. Somebody do it on their calculator so you can help me out here in a minute. On bottom, it's going to be 43 minus 3 factorial. I don't know why I made my fraction bar so long there. 43 minus 3 is 40. So we got 40 factorial on bottom, 43 factorial on top. So if I start to do this, 43 times 42 times 41 times 40. Do I really want to list all those out all the way down to 1? That's going to be too much, isn't it? Times 1, going all the way down. Well, on bottom I got 40 times 39 times 38, so on, so on, so on, all the way down to 1. What's going to happen from 40 down on top and 40 down on bottom? It's just going to cancel out. So all I'm really doing for the permutations is what? 43 times 42 times 41. If you can figure that out, about half the time I don't even use the permutations button on here because it annoys me that I always forget to put in the number first. So all I really have to do here is 43 times 42 times 41 and get 74,046. How many different ways are there that the drivers could finish first, second, third in that Daytona 500 then? Let's do this. I'm going to tell you in that race, the number 5 car won, the number 32 car finished second, and the number 19 car finished third. What's the probability of that event occurring? 1 out of that. 1 out of that 74,046. There's only one way that those 3 cars could have finished 1, 2, and 3. That was funny. Fundamental counting principle, that's what we were just talking about. So if we're using the fundamental counting principle, what ends up happening is that so much of the top and bottom end up canceling out. So sometimes just using the fundamental counting principle makes it easier. Given the list, watch on this. This is a little more difficult. Given that list, 4 A's, 2 B's, and a C, find the permutations. So we want all the permutations. How many letters do we have to pick from? 7. And we're taking all 7 at a time because we're just finding the total. So on your calculator, somebody do that for me real quick. 7P7. 5,040. Now the bad thing with this, if I was going to start listing out all these permutations, my first permutation might be that one right there. my second permutation, I'm gonna switch these two letters. So now my second permutation looks like this. What do you notice about those two? It looks the same, doesn't it? Even though what I do with these two A's, I switched them. Alright, now let's do it. Yeah, I'm positive I did. Watch, you gotta watch close, Malachi, or you can't see me switching. Now the next one, I'm gonna take this A and that A, and I'm gonna switch them. Are you watching, Malachi? You gotta watch real close.
I'll watch it.
So I switched these two A's this time.
Looks the same to me.
So it looks the same, right? But what did I do?
Flip-flop.
I switched those two A's. Then I'm gonna switch this A and this A. Are you watching, Malachi? Watch. See what I did? Michael, is he finally catching on that I'm being a jerk?
You're always.
I know, I'm always a jerk, but I was really being a jerk this time. What do you notice about those? They all look exactly the same, even though each one's a different, no, each one's a different permutation, because I took that first A and moved it to the second spot. I took the first A and moved it to the third spot, but they look the same. And that's where we need to be able to do this, be able to find distinguishable permutations. Permutations that are different from each other. All right? On this set, if we're taking all of these and we're trying to find different permutations that are permutations that are completely different, there's a certain way you got to do it, and that's what we're going to learn next. So, finding distinguishable permutations where we're not listing this, 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 and this because they all look the same. So we'd want to do away with those. We wouldn't want them as part of our final answer. Thought I had the formula up here next. Maybe I don't have the formula. All right, distinguishable permutations. Write this down. Somehow it got left off my PowerPoint here. We're going to write a formula for that. Distinguishable permutations. Write that down. Make sure you write it down correctly. It's sort of hard to understand. You're going to have to be able to do this. There's going to be several questions on the next test that deal with distinguishable permutations. Malachi might want to help Jake about poking in the back.
Sleep.
Pretty good.
So if I'm doing this problem,
30 hits.
Soon as 30 hits, he said it too.
5,440 different ways, different permutations that we could put those letters. But if we want all the ones that just look different, so we want this, then we want one like that's a different permutation. That looks completely different now, right? If we want just those ones that look different, ones that we can distinguish separately, this is the way we do it. We do n factorial on top. How many letters do we have?
7.
So we do 7 factorial on top. And then we look at each 1 by itself. So the first one, N1, how many A's do we have? 4. So we do that. On bottom, 4 factorial. How many B's do we have? So we do 2 factorial. How many C's do we have? So we do 1 factorial. And I'm going to tell you, if the item only appears once, you really don't need the 1 factorial. But if it helps you to make sure you get everything, then put it in there. Because what is 1 factorial? Just 1. So now we got 7 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 factorial, which is 4 times 3. You can't do these out on the calculator this way. Times 2 times 1. If you're looking for distinguishable, it won't work on the calculator. Then we got 2 times 1 for the 2 factorial. For the 1 factorial, we got 1. I'm just going to get rid of that. We don't need it. What we can do to make this a little easier on ourselves, cancel some of this out. 4, 3, 2, 1. 4, 3, 2, 1. You can get rid of that, right? So now what we got to do is 7 times 6 times 5 on top. Somebody do that for me. What's that give us on top? 210. On bottom, we got 2 times 1, which is what? Divide that. How many different permutations are there of those letters right there that we can tell the difference? 105. It's a big difference from 5,040, right? So there's actually only 105 different ways we could situate those letters where they all look different.
Why do we have an extra 2 times 1 on the bottom?
There, we took,
That's the B.
that was our B's. So we had, there was 4 A's. So we'll do another one, and I'll show you on that. A building contractor is planning to develop a subdivision that consists of 6 one-story houses, 4 two-story houses, and 2 split-level houses. And how many distinguishable ways can the houses be arranged? So if we were just doing permutations, we would do P. How many total houses does he have here? 12. How many houses is he building? Or how many are we taking? All 12 of them, right? Somebody on your calculator do that real quick. What's 12P12?
479
Let's just say that. 479 million?
Yeah.
Everybody agree with that? We'll just go with that. 479 million different ways that he could put these houses in this housing complex. All right? You've probably seen, I know down there where I live at, there's a lot of these housing complexes, and you see this house, and then they screw up, and the house right next to it looks identical to it because they didn't change anything around. But then throughout the whole complex, there's all kinds of different houses. So they're trying to make sure that they don't put this house and this house look exactly the same neighbors to each other. So there's 479,000 different ways. But we want to make sure that we don't do that. That we don't put all the 2-story houses right here in one area, all the 1-story in one area, because then they're all going to be next to each other. So we want the different or distinguishable permutations, the way it's going to look different. And this is where it's going to come in, Sophie. So what we're going to do is we're going to take each one of these. We know that we have 12. So we got 12 houses, factorial on top. On bottom, we got 6 one-story houses. What a stupid thing. So we got 6 factorial. We're going to divide by that because we want them to be separated. Times, then we got 4 two-story houses, so 4 factorial. And then we got 2 split-level houses, so 2 factorial. Now if I expand this all out, give me a second, 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's all on top. Now here I do these. I got 6 times 5 times 4 times 3 times 2 times 1 times the 4 factorial, which is 4 times 3 times 2 times 1 times the 2 factorial, which is 2 times 1. So I can 6 through 1, I can cancel out here and there, right? Now do we just have to do all the multiplication from there? I would do something like this. What's 4 times 3? Can't you do that and cancel that out? Yeah. Here, what's 2 times 1 times 2 times 1? That's 4, so that's not really going to cancel out with anything else, is it? We could cancel it with the 8 and make the 8 a 2 or something like that, but it's probably better just to, somebody do this, multiply those together for me. 440. And then on bottom we got 4, so we're going to divide that by 4.
13,860.
Is that a big difference from the 479 million that we had up here? Yeah. When we want them to be different, so if John and Joe, they both buy 2-story houses, and we want to know that they live in different areas, they're not one here, then switch around one here. A lot of different permutations there. So this is distinguishable permutations. If we're not worried about distinguishable, if I take these 3 books and we just want to know how could we stack those books on the shelf, all right? We're not worried about whether it's distinguishable or not. How many different 4-letter words can be made from the word statistic? You might want to watch this one real closely. So we want 4-letter words. So if we were doing permutations, how many letters are we picking from? 10. How many are we taking at a time? 4. Somebody do that on their calculator real quick. 10p4. 5,040. Have we seen that number before? You'll see a lot of these numbers, they repeat themselves for permutations and combinations. So we got 5,040. But how many different 4-letter words? Well, if I wrote this one, then I wrote this one using that S, are those different? Not really. All right, same word, right? So if we want it to be where they're distinguishable, where we're not repeating that same word over again because we have a bunch of S's, then we do it this way. 10 factorial on top. We look at each letter. How many S's do we have? So we do 3 factorial times, how many T's do we have? So 3 factorial again. How many A's do we have? Do I really need to list the 1 factorial? T's we already did. How many I's do we have?
2. And 1C.
1C. Do I really need to list that? And we could just use your calculator and do this. You could do 10 factorial. Have that number, then divide it by, here we got 3 times 2 times 1 times 3 times 2 times 1 times 2 times 1. Do we really need these 1s on the bottom each time? Not really. 3 times 2 is 6. 6 times 6 is 36. Times 2 is 72. Somebody use their calculator and help me out. What's 10 factorial?
3 $3,648,800.
Now, I'm not gonna write that number down because you got it right there on your calculator, right? What are you gonna divide it by? 72, so divide it by 72. 50,400. So how many different four-letter words could we make from the word statistics? 50,400. Now notice I didn't say four-letter words that make sense, because that's a four-letter word. It's not really a word in our language, but that's a four-letter word. Combinations. Combinations a little different. Right quickly because we're going to run out of time. Combination, n objects taken r at a time, a selection of objects from a group of n objects without regard to order. And I hate it when I give the definitions of these, because that seems to confuse people a lot of times. So if I tell Miss Clark, she's got my 9 books here, and she can take 3 of those books to read. She loves to read. She can take 3 of those books to read. Is it going to matter if she picks this book, then this book, then that book? That's one way she could pick, right? Next time she picks this book, and this book. It's the same thing, isn't it? So instead of permutations, because she could pick, for permutations, for picking those 3 books, but what order they were in made a difference. That was a different permutation. For combinations, it makes no difference. And that's what we're getting rid of. Notice that you have this extra part right there. So you're dividing by r factorial to get rid of those extra ways that you could take it. State's Department of Transportation plans to develop new section of Interstate Highway, received 16 bids from the for the project. The state plans to hire 4 of the bidding companies. How many different combinations of the 4 companies can be selected from the 16 bidding companies? So Lucas has a company, Sydney has a company, Katie has a company, Michael has a company. They all want to be picked. Does Lucas care if he's picked first or last? Does it matter to him? No, he just wants his company to be picked. All right? So unlike permutations is more dealing with, think about a race. Because in a race, where do you want to finish? First. Permutations, first, second, third matters. Combinations, first, second, third makes no difference. So if Lucas is picked first or he's picked third, he don't care. As long as his company gets picked, then he's got to work and he can do the job. So we do this. Order isn't important. On bottom now, you got that R. You're going to take that 4 factorial on bottom. Again, if you use your calculator, what all you punch in for your calculator is that right there, but you're using C, and it'll do it for you. All right? Notice, if we wrote it out longhand, some of this stuff cancels out. 1,820 different combinations. 1,820 different ways that 4 companies could be picked.